Okay, so today we are happy to have Kathryn Zurek, who will be telling us about from shockwaves to gravitational memory approaches in flat space holography.
Thanks, Juan, for accommodating my visit. I want to tell you a little bit about a program I've been working on the last several years. And focus on some of the technical aspects that we've been working on over the last year. And but I got into thinking about this because I was interested in observational signatures, but I'm not going to talk about observational signatures until the end of the talk. All right, so what am I trying to get into? It's understanding space-time fluctuations. And ultimately, whether there might be some UVI or mixing effects that could make them visible in experiments. And of course, we all know that the conventional view is, which we understand from effective field theory point of view, is that fluctuations in quantum gravity are not observable. So the Planck length is at 10 to the minus 35 meters, 10 to the minus 43 seconds. And these are length and time scales that are really much, much too small to be observable in any type of an experiment. But there have been a lot of developments in the last 10 years. And I'll see if you disagree with me if I say that okay, all right, so I'm going to take advantage of this short window for as long as it lasts. All right, so I wanted to know whether UVIR could appear in, there it goes. Could appear in some type of observable. And what actually got me inspired to look into this, well, this isn't entirely true, but there's an example that we know in the literature. And it's not, for some reason, the one part of the screen is getting cut off down here. But anyway, actually dates to an example from Don Merrill in 2003. And what he did in 2003 was he asked about a black hole horizon. And he said, let me take this idea of the entropy of the black hole and think about those degrees of freedom as pixels that can fluctuate. So this picture is from his paper. He said, well, let me imagine that I have an entropy's worth of degrees of freedom, and let me allow them to fluctuate with a typical temperature that's set by the size of the black hole horizon. So you should think about this like in the canonical ensemble. And he said, okay, if these bits now are all allowed to fluctuate with a temperature of this size, this means that there will be thermodynamic fluctuations. And those thermodynamic fluctuations will change the effective mass of the black hole. So we'll see if this is stable. So I was talking about this example from Don Merrill from 2003, where he was looking at the entropy of a black hole. And he was asking the question, if I think about this entropy as pixels that have a typical temperature that's set by the size of the black hole horizon, and then I allow for fluctuations as in the canonical ensemble. So this is a picture from his paper. So I can think about these bits as fluctuating from up to down. So they're just going to have ordinary root n type fluctuations. And that will be an effective change in the black hole mass. Think about it that way. And that effective change in the black hole mass will give rise to a back reaction that will actually shift the position of the horizon. And he computed what the shift in the size of the black hole horizon was. And because it depends on the number of degrees of freedom, thermodynamic degrees of freedom, it shouldn't be too shocking that the result that you get at the end of this depends on the size of the black hole horizon. So it turned out that in this example, he didn't write it quite this way, but it's equivalent, that the uncertainty in the position of the black hole horizon, which is to say the fuzziness of it, depended on the UV and the IR scale. And if you just write it out more generally, it depends on the entropy of the black hole. So this is, maybe theoretically interesting, but it wouldn't be observable at all. So it'll turn out that the observational signatures that I've been interested in now for horizons in empty space, they'll mathematically function similarly to this. Okay. So now I'm just going to put a sharp break, okay, even if you really dislike this, because everything that I'm going to say for the most of the rest of the talk is going to be independent, can function independently of this. Okay. So I'm going to focus on some technical results because there are some pieces that go into this. I'm not interested really in black hole horizons. I'm interested in flat space horizons. Flat space horizons that are created by light sheets. And I wanted to understand whether some of the technical things that are going into this type of a calculation one might expect to apply to flat space horizons. And to do that, I've been working on some technical aspects that I hope that by the end of the talk, you'll see what the connection is to this picture. So the first thing that I'm going to talk about is some work that I've done with Tepal He and Ana Maria Reclariu. We have some more work in progress where we showed that the shockwave metric that dates back to Hooft from the 80s is actually diffeomorphic to this memory metric that people work with in the context of the celestial holography program. Okay, so as a consequence of this, I'm going to show that shockwaves can be understood as a gravitational memory effect. And furthermore, that the quantum mechanics of the memory modes that's part of the celestial holography program is actually equivalent to the quantum mechanics of shockwave operators. So if you're comfortable writing down commutators between news and shear, you can actually show that that's technically equivalent to, it's diffeomorphic to the commutator between light ray operators. So that's the first point. Then I want to use this last point, the quantum mechanics of the shockwave operators, to show that if you have a particular commutation relation and you're in a minimum uncertainty state, that implies something that's analogous to modular fluctuations that are known in ADS-CFT, that they actually appear in flat space-time. So I'm just going to follow this logic through to here. Okay. And so then with this result here, I'll show that those modular fluctuations go like a 4-point function of these light ray operators. So if you just do a naive back of the envelope, it allows you to estimate the size of space-time fluctuations. So I'll do that. Now I'll caution once I get to this stage that what I've computed is not, strictly speaking, gauge invariant observable. But I'll talk about why I think that it's connected to a gauge invariant observable. And then this last part, okay, which I may not have much time to get to at all, is if there may be observational implications. Okay, but I'd like to emphasize that these first 2 points now are prior to this last statement. All right, so part 1 is this work with Tepal and Ana. So this is the setup. It's shockwaves and then Hooft commutation relation. So what Hooft did was he was interested in black hole horizons, and he said, okay, if I have a particle that's going into the horizon and I have Hawking radiation that's coming out, the energetic particle that's coming in that has some typical momentum is going to give rise to a shift in the position of the outgoing radiation. And this is just an Einstein equation right here. It depends on a green function of the transverse Laplacian, which in 4 dimensions, that green function is just a logarithm. And then you have the metric sitting on the transverse directions, which are going to be called z and z bar. So this is just classical. What Tufte did was to promote these operators to just be this momenta and position now of particles, okay, that have classical meaning, to a commutation relation. And I'm not going to actually try to justify his reasoning for this. You can write down a shockwave effective action where these very naturally become the conjugate set of operators. But I'm just going to say this is what he wrote down, that there's a conjugate pair of momenta and position, because x minus, when you lower it, becomes x, p minus and x minus. The blue pairs here are the conjugate pairs. And he said, these are going to have a commutation relation that just depends on a delta function on the transverse directions. This I'm going to show is actually equivalent to a commutation relation that may be more familiar in celestial holography. So I should say that it had been previously suggested that this commutation relation applies near generic light sheet horizons, even in flat space. This actually dates back to the Verlindes, a paper they wrote in '93. But what we want to show is that there's a diffeomorphism that takes you from the shockwave metric with those commutation relations to a commutation relation, which comes from the Poisson brackets between the shear and the newts, which are sometimes called the Goldstone mode and the soft mode, okay, which if you open up, say, lecture notes by Andy Stromander, take on a form that looks like this. So now you have something that depends on the time. So that's going to end up working out because we'll be integrating the news with respect to one of the time variables. All right, so that's the result. Let me give you a few more details. So the shockwave metric, written in light cone coordinates, takes just the usual du dv or dx minus dx plus. And then there's a metric on the transverse directions that depends on the radius of the celestial sphere. And then here's the perturbation that's being put in due to the energetic particle that's causing this shift that I showed before, that's being parameterized in terms of this function alpha that's on the celestial sphere. So you can write down Einstein's equation for this energetic particle, and it just depends on the transverse Laplacian acting on this function alpha. That depends on the matter stress tensor now for the energetic particle that's propagating at some point in time. That's the shockwave side. Now on the memory side, okay, if you open up one of the celestial holography papers, it takes this form. They usually don't use x plus and x minus. They use u and r, where u is actually, I think in this notation, equivalent to x minus. So it's written in terms of the unperturbed metric. There's typically a Bondi mass, which for the purposes of this analysis, we're going to drop the Bondi mass and generalize it, which is one of the things we're doing right now. And then there's a perturbation that's written in terms of the shear. Okay. And the shear is written, is related directly to the news. In particular, if you write down the UU component of the Einstein equation, the news is just directly related to the stress tensor. Okay, so what that tells you then is that the gravitational radiation, if you write down the Einstein equation, the gravitational radiation that's characterized by the news causes a change in the shear. So this is, at this point, just a classical statement. So the picture that you often see is you have the world lines of two detectors, and you have some gravitational radiation, let's say from a gravitational wave. it comes in and it shakes these detectors. And the separation of those detectors at the end is different than their initial separation. And that's what's usually called the gravitational memory effect. And you can just, and this is encapsulated in this Einstein equation where the initial CZZ and the final CZZ, the shift in that is just due to the news, which is characterizing the incoming gravitational radiation. So at least at the level of words, you can start to see that if I were to look on the two sides of the fence, okay, the shockwave side of the fence and the memory side of the fence, you can see that there's an analog between the incoming particle momentum, the radiation, the momentum of the incoming particle, and the news, which characterizes the gravitational radiation on the memory side. And the light ray shifts that are the results of this incoming particle, and the shear, which is change, which characterizes the separation between these detectors, that's changed as a result of having encountered the gravitational radiation. Okay. So the thing to keep in your mind is the map is P and the news are just directly related to each other, and the shifts and the shear are also directly related to each other. So to actually work this out, you have to find the diffeomorphism that respects the conditions of the Bondi gauge, because both the shockwave and the memory metrics are in the Bondi gauge. So you have particular conditions on the metric that have to be satisfied. And so it turns out that there's a diffeomorphism that preserves these conditions that can be written in terms of just one function. That's the function that generates the super translations. And that function here is called F. So now you can crank this through. And the diffeomorphism that I wrote down on that last line now is able to transform the shockwave metric into a form that's not exactly the Bondi metric, but it's closely related to the Bondi metric. There are some additional terms that appear in here. And it turns out you can show that the symplectic form and therefore the commutation relations that you end up writing down are not changed by adding in these additional terms. We get the same symplectic form. So now that diffeomorphism allows you to relate the quantities on the memory side of the metric to the quantity on the shockwave side of the metric. And therefore, the momentum of that incoming particle to the news associated with the gravitational radiation. And likewise, there's an even simpler relation. There's a coordinate shift under super translations, where the coordinate is shifted by this quantity, which is the shear. And so therefore, these shifts in the light ray operators, I can just directly associate with the shear. And so now I have the ingredients that I need to take this tough commutation relation between P and X via the diffeomorphism to relate it to the news and the shear, to pick up from the literature what this commutation relation is, to plug it in. It depends on some function on the celestial sphere, and then there's this transverse Laplacian in 4 dimensions. And so when you crank this through, it turns into exactly that 2-dimensional delta function on the transverse directions.
So I think I got lost on how P and X were defined.
So P and X, so that comes back to the very first slide. So I have the momentum.
P and X is for a single particle.
Yes.
Supposed to be integrated over all particles.
So you can integrate it over a collection of particle What I've written down here is just for a single particle, single energetic particle. It would be straightforward to write down some distribution of particles and define a momentum operator, which would be.
So there's an operator that depends on C, right? In the formula.
Well, this is the shockwave side of the metric, so there's no shear here.
The formula that I asked about just a moment ago.
This formula?
Yeah, so there is a P of C and C bar, right? P minus of C and C bar. So normally the momentum of a particle is just the number, it doesn't depend on C and C bar.
Because it's propagating at a particular position on the celestial sphere.
Is this supposed to be like the integral of the stress tensor in the minus direction?
Yeah, so generally speaking, if I have some momentum, it's going to be, it'll have some position, the transverse directions. It'll be coming in at some time, and then it'll have some momentum, whatever you want to call it.
Is this an operator in the quantum field theory?
So
is that supposed to be like the integral of the stress tensor along the minus direction?
Yes. Yes. Yeah. Exactly.
I think I understood what P is.
Yes.
What is X minus?
So X minus is going to be
I understand for that single particle case, but is that supposed to be an operator in the?
So when you promote it to an operator, so when you promote this to an operator, so you can write down these shifts in terms of the integral of the metric, which then you can rewrite in terms of the stress tensor.
Some integral of the metric.
These shifts, yeah, are an integral of the HUV or the HVV component of the metric along. So what it does is to tell you about the shift with respect to the unperturbed light trajectory.
Is there some intuitive way of understanding this mapping by telling this detector story in terms of shockwaves? You have these two detectors and then some shockwaves by.
Yeah, exactly. You just on this picture, if I can find it. Guess it was the other way. I just replaced the words radiation, which is really just news, just replace it with momentum. It's P, it's the momentum of the incoming particles.
And so I would have thought, I guess incorrectly, that if you have some shockwave coming by, it would shift both of the detectors the same amount in some direction and not change the distance between them at the end.
So they're not encountering the shockwave at precisely the same time. So you do get a shift of one detector with respect to the other. So the kind of classic example, if I want to put it in like real space, if I've got a celestial sphere, and then I've got two detectors sitting on the celestial sphere, and then I've got a spherical shock incoming, what's going to happen to those two detectors is they actually get shifted in opposite. They get shifted apart.
Oh.
And the way that the people who work on celestial holography talk about that is that there was a change in the shear that just directly maps onto the shift in those detectors.
Interesting. Okay. Yeah, thanks.
Yeah, since people are asking questions, so the P and the X in your earlier slide was you had an horizon. That is the shifts typically in the Hooft story.
Yes, they're exactly that.
The horizon.
Yeah.
Because the news and the C's are typically defined as celestial sphere.
Yes.
So there's a translation.
Yeah. So what I'm
to infinite radius.
Exactly. So I'm regulating the celestial. So in my mind, I'm always taking that celestial sphere from scry plus and scry minus to some finite radius. But there's a 1 on R expansion that I can make. And I'm always just taking the leading component the leading piece in the 1 on R expansion.
Which
As
means,
long as the radius of that celestial sphere is much bigger than any of the other length scales in the problem, which in this case, the only relevant length scale in the problem is the Planck length.
Right.
And so therefore that ends up being a very good expansion. So yes, I'm always imagining that I'm pulling in that celestial sphere from infinity and putting it at some finite radius. All right, so our conclusion was that there's a diffeomorphism that relates the memory and the shockwave metrics. And so therefore the momentum of energetic particles to the news of the gravitational radiation. And likewise, there's a relationship between these shifts in the light ray operators and the shear C. So if you just crank it through, then what it says is that this tough commutation relation is just equivalent to the standard soft commutation relations that already appear in the literature. So if you're willing to reasonably promote the Poisson brackets that appear in celestial holography, then these tough commutation relations now in flat space are standing technically on the same ground. It's still an ansatz about the way that you quantize the theory, but nevertheless, the claim is that these are now on the same ground. So now I'm going to move into the second part of the talk. So I want to say one more thing about that. So another way you can write those commutation relations between P minus and X minus upper is to use the equation of motion, where the shift in the position of a particle is related to the momentum of the incoming particle. So in this case, we're looking at this pair where I have an outgoing particle and I'm looking at the shift X plus and the radiation that would be dropping in, okay? So this is just the Einstein equation. And if I plug in this relation between X plus and P minus, what it gives me now is a commutation between the light ray operators. Okay, X plus and X minus, that now just depends on this green function of the transverse Laplacian, and of course there's a G Newton sitting in there. So now what I want to do is to take this commutation relation, take it seriously, and try to understand what I might be able to extract from it. Skip this slide. And that was the content of this paper that appeared about a year ago. Actually working backwards in time. So with the tough commutation relations on a similar footing as the soft commutators, let's look at the implications of this relation. So if these operators are Hermitian operators, there's a Robertson uncertainty relation that relates this, the uncertainty in these operators to the commutators. And now let's look at this in the context of now shockwave physics. So I'm going to rewrite the shifts, and this maybe is going more directly to your point, is that these shifts and the light ray operators are just related by the equation of motion, which is just the UU component of the Einstein equation. And now I'm writing the transverse Laplacian in terms of delta sub y. So y is now my transverse derivatives. And that's related to the stress tensor of the energetic particle now, C++. And this equation of motion, this is actually, you can write down now an action that would generate this equation of motion. And I think it was first written down in this paper in '93. And the shockwave action that would generate that equation of motion, you can just call it an effective action, depends on the product of these light ray operators. And you can just quickly check that, as you would expect, the on-shell action vanishes on both the lower and upper parts, on the lower and upper parts of this causal diamond. However, there is a contribution from a surface term. And that contribution from the surface term that appears when integrating by parts looks like this. So now the term that you get has this minus sign, it has a 1 on 8 pi g Newton, and depends on these transverse derivatives. So if you combine it with the equation of motion, okay, which identifies one of these shifts with the stress tensor, what we did was to notice that this horizon contribution to the action actually looks like a product of a shift with something that looks like the stress tensor, and then integrated over the transverse directions. So the reason why that is suggestive is because the modular Hamiltonian is written down in terms of a product of the stress tensor times a conformal killing vector integrated over the relevant volume. It takes the same form. It looks very much the same. And so what we did was to identify this horizon contribution to the action, the effective action, the shockwave action, with the modular Hamiltonian K. And now we want to evaluate what the expectation value of this operator and its fluctuations are, assuming the Hooft uncertainty relations. So that's what we have. So we're identifying these product of light ray operators with the modular Hamiltonian. And then what we're going to do is to use the Robertson uncertainty relation to extract a 2-point function of x plus and x minus. And we're going to evaluate it in Euclidean space. So let me say a little bit more about this line.
This is supposed to be the modular Hamiltonian of the wedge.
Yes.
Where is this x plus and x minus defined? Are they defined at infinity? Or are they defined on the horizon?
I would on the horizon, on the bifurcated horizon. So recall that I can choose a gauge where these shifts are written down in terms of an integral. If I have an infinite size causal diamond of an integral of the metric, say the HUU metric with respect to the time coordinate. If I have an infinite size diamond, I can integrate from minus infinity to 0, where 0 is the bifurcated horizon. So that statement, the way I think about that is I'm defining the shifts now on the bifurcated horizon. And likewise, I have the other part. So if that's x minus, and I have x plus, I do the same procedure on the upper part of the causal diamond. And then the place where this relation is actually defined is right on the bifurcated horizon.
The x minus and x plus are shifts of the bifurcated horizon.
Yes, correct.
I mean, K is supposed to act on the matter that, for example, if I have an operator in the wedge, K is supposed to act.
Yeah, that's right. So the thing that you're asking is, well, if I have empty space, so this is where there's a leap. So and we're working to close this up technically right now with Anna and Temple, but let me just tell you how I think about it. So you might say, well, I have empty space time. There's no energetic particles. That's what, because I'm going to evaluate the vacuum expectation value. There's no energetic particles. What are these shifts of? And what is that the stress tensor of? And the way that I think about it is that the vacuum is fluctuating. As the vacuum is fluctuating, there's a non-zero stress tensor. That non-zero stress tensor now induces shifts in the propagation of the light. And so
I was
therefore,
asking a more elementary question.
okay,
If I have some operator that normally modular can act on some operator. And one would expect it to act like a regular time translation. Just
yeah.
was wondering whether that fact can be deduced from this formula.
So these shifts are directly related by the equations of motion to the stress tensor. So what I have here is if I do an integration by parts, I pull one of these transverse derivatives, I get a transverse Laplacian acting on X, that gives me the stress tensor. So what you should see when you look at this formula is there's a stress tensor multiplied by a shift integrated over the transverse directions. That shift is doing the same thing as the conformal Kelling vector. It's actually,
That's some operator, the shift. Maybe I would expect.
Yeah, so-
expression which was.
yeah, that's right. So we're also effectively promoting the conformal Kelling vector to an operator. If you think about it that way.
The question I think is that x minus when you express it in the stress in terms of the stress tensor is an integral. It's an integral over a like direction of the stress tensor. That's correct.
Yes,
So indeed, this in the end, once you plug in the stress tensor, it's actually a three-dimensional integral.
correct. Yeah, that's right. It's a three-dimensional integral. And then,
X plus multiplies.
correct.
But it's what's maybe less obvious is that it then becomes the generator of a books.
But it should be the integral over x minus, or t minus minus times x minus.
Or t plus, yeah, or one of the two.
T minus minus times x minus, right? So if we go back and then there'll be a three-dimensional integral. So there'll be a d squared y, a du.
The problem is that the x minus multiplies is not an operator, but just a coordinate.
In the usual picture, it's just a coordinate. Here we're promoting that coordinate and the coordinate shift to an operator. And that's actually very similar to what's happening in celestial holography, because you have the super translations generate shifts. X minus goes to x minus plus c. And so now if you write down a commutation relation for c, you're promoting c, the shear, to an operator. And the analog of that here is the Kelling vector. Yes, we are promoting a coordinate to an operator. So we have this expression for the modular Hamiltonian. I should say we have this expression for the horizon contribution of the action that we are identifying with the modular Hamiltonian. And now we want to compute the expectation value, vacuum expectation value of this operator. So here we're going to use this relation that the vacuum expectation value of these operators in Euclidean signature is given by this relation that comes from the tough commutation relations. So let me justify that a little bit more. So these light ray operators, x plus and minus, are permissions. And so x plus and minus now are r plus or minus t. So now if I rotate, if I continue to Euclidean signature, in Euclidean signature, these operators are now anti-Hermitian operators. And so there is a basis that you can choose where these Euclidean operators are now raising and lowering operators. So only one of the operators acting on the vacuum state gives a non-zero contribution. So what that implies is that x minus expectation value would vanish, for example, but I would get a non-zero contribution from x plus x minus. So now let's evaluate that. So the modular Hamiltonian now is this product of light ray operators. I can do an integration by parts to pull the derivatives onto, say, one of the operators. And now I can plug in this expression, which comes from the tough commutation relations. It just depends on G Newton in a way that's totally unsurprising, times this transverse green function in the transverse Laplacian, okay, which I've just, for reference, written down here. So if you just take the vacuum expectation value of both the left and the right-hand side, that expression, what you find is that you get a divergence from this delta function. And so you have to do something with it and regularize it, which is very similar to what you do when you compute the entanglement entropy in CFT, for example. And you're just going to replace this transverse delta function with some UV scale. Let's choose it to be the Planck squared. So then when you evaluate it, what happens is you're going to still have a transverse integral left over. That's going to give a factor of the area divided by some divergence. So let's follow tradition and choose it to be 4G Newton. Similarly to what you do in calculations of the entanglement entropy. Okay, so you get something that is area divided by divergence squared. So now let's compute the fluctuations in this operator. And let's assume that these fluctuations of the modular Hamiltonian are Gaussian, in which case the 4-point function is going to decompose into a product of 2-point functions. So if you compute the variance, k squared minus k expectation value squared, the only term that's left over is the product of these light ray operators. So now you can crank through in exactly the same way. And what you find is that it's, again, these fluctuations now go like the area. And the form, I think the most important thing here is that the form of the divergence is exactly the same as for the expectation value of k. So if you fix the divergence to be 1 on 4G Newton, that means that the divergence that's going to appear here is going to be exactly the same. And so what you find is that this k, the expectation value of k and its fluctuations, they both scale with the area and have the same divergence, which I've decided to set to be 1 on 4G Newton. So the line of reasoning is start with the Hooft or celestial soft commutation relations, write down the shockwave effective action, identify the non-zero term. And if you identify that shockwave effective action with the modular Hamiltonian, you reproduce this result. So this is familiar from ADS CFT. And the modular fluctuations in ADS CFT have been calculated in multiple places, and it's known as the capacity of entanglement. This quantity right here, the fluctuations in the entanglement entropy, are known as the capacity of entanglement. So what's done there is that you have, in that case, the modular Hamiltonian is the CFT stress tensor. You have this conformal killing vector, and then it's integrated over this volume here now on the boundary. And you can either calculate this quantity on the CFT side, or Perlmutter did that, or on the gravity side, and they all yield this result. So at least from a physical point of view, I don't find this surprising that these fluctuations in modular Hamiltonian or the soft effective action would give rise to this area law that respects this relation. But maybe I think some people do find that surprising.
The pure CFT result is the left equality, and then the other one is the root eigenvalue. If the CFT result is just the left equality.
The CFT result is the whole thing.
CFT result, I think, isn't it just the K
Delta.
expectation is delta K squared, and then your A of sigma is your minimal service. So that's root eigenvalue.
Yeah, it's for your talking now. Yeah. Sorry. All right, so what is the physical meaning of the modular fluctuations? So in the absence of gravity, I don't think entanglement entropy has physical significance. I don't think it's an observable. But in the presence of gravity, the modular fluctuation, which is the variance from the entanglement entropy, we studied this in this paper, and we found that the fluctuation in the modular Hamiltonian actually gives rise to a shift in the metric. So it sources metric fluctuations. And so the previous calculation suggests that the same relations hold in flat space. So now let's do, I'm going to call this naive dimensional analysis. So if you take those modular relations, the shifts, these shifts and the light ray operators are related by a derivative. There's a gauge where you can take a transverse derivative on these light ray operators and relate it to a component of the metric, a transverse light cone component of the metric. Okay, I'm going to call this a mixed gauge. Now, interferometers measure something that is closely related to these shifts. And the reason for that is that these shifts can be written in a gauge where you do an integral along some light ray of the metric perturbation. And there is a gauge you can choose where these shifts are exactly the shift in the fringe of a light front that you observe in an interferometer. Okay, that's the TT gauge. Okay, there's also the proper detector frame where you would put it only on the mirror, but in TT gauge, this is the observable. So now let's do a little bit of an estimate. So this operator is the one that entered in the modular Hamiltonian. Unfortunately, none of these calculations give me the global metric. They only give me the integral of the metric along this trajectory. They only give me the amplitude of the shift. So unfortunately, that's not enough information to compute the proper gauge invariant observable. I will just tell you what I think the weakness of this is. It is not enough information to compute the proper gauge invariant observable. However, you can just estimate the size of the effect. So if you take this and you say, okay, I'm going to average over the transverse directions by integrating over the transverse directions and dividing by the area, this quantity on the right-hand side differs from the modular Hamiltonian by a factor of the Planck length. Now, if we put it in some arbitrary number of dimensions, it's d to the d minus 2 divided by the area. So parametrically, now I can evaluate this. This quantity, which was just the quantity on the previous slide, squared, I get this L Planck to the D minus 2 divided by the area. Now I have to square it times the modular fluctuation squared. So now if you look at that, everything now here is totally normal in terms of G Newton.
Expectation value around the delta K.
Yeah, that's right. Yes, that's right. Thank you. So that gives you an area on G Newton. So parametrically, that cancels one of these factors. And so you get one factor G Newton divided by the area that's left over. So if you just look at this parametrically, the reason why you end up with a funny scaling is because you have a 4-point function that scales like G Newton. And the reason why you ended up with G Newton and not G Newton squared is because delta K squared has a 1 on G Newton in it. And if you want to think about that physically, what it's telling you is that if this effect, if it's there, it's not a single graviton effect, it's a coherent effect that's coming from the emission of a large number of soft gravitons. And that's why you get this additional factor of 1 on G Newton. And that's why the scaling was funny. So if I just evaluate this now, I'm not going to, this is not a proper gauge invariant observable, okay? This now just goes like 1 power of G Newton. Now I have to take the 1/4 power to pick up the size of the length fluctuation. And so that's why I end up with the scaling with square root of L Planck.
In the end, we are computing the motion of some detectors, right? We can compute.
Well, it depends on what gauge you choose. You can use it.
Well, let's discuss the physics first without any gauge. We are computing some what LIGO will detect.
Right, but what LIGO will detect depends on the sum of 3 effects. Depends on the clock, depends on the photon change in the photon trajectory, and it depends on the mirror motion. And of course, how those enter into the calculation will depend on the choice of gauge. But strictly speaking, there are 3 effects that enter into the LIGO observable.
Okay, so I compute something that is whatever appears in the readings, the sigma.
Yeah.
So that's gauge invariant. And
Yes.
in principle, in the effective field theory, we compute this by Feynman diagrams and so on, which have powers of G Newton.
Right.
So I think in that language, one should see why. Well, so that calculation, such a factor of the calculation, such as that it did not have an effect like this.
Correct.
And so
So
there has to be something wrong in this calculation.
Yeah, so I think there are various ways of thinking about it. One is that the Feynman diagram calculation involves single gravitons, and this is not a single graviton effect. It would be like if I went to my material, if I have some material, let's say a crystal, and I displace some atom, and then I compute a Feynman diagram with the process where I've displaced that atom. But then I forgot about the fact that the effective field theory description says I have to actually look at the oscillation of many atoms, and therefore I'm computing it with the wrong degrees of freedom. So if you compute a Feynman diagram with gravitons, it's just the wrong degrees of freedom. So I think that there will be a Feynman diagram calculation, but I think you need to be looking at collective modes. And so that's one of the reasons why I'm excited about the celestial holography program, is because it has these collective modes in there. There's these soft modes and these Goldstone modes. There's these edge modes. None of these are like single graviton degrees of freedom, they're collective modes. And so I think if we're going to find the effect, it's going to be from looking at that soft effective action and then computing processes with that soft effective action.
Celestial holography discussion, do computations using Feynman diagrams.
Yeah.
Like this with the things that they compute.
If you,
if
if you compute it in the ordinary field theory vacuum, but now you have a large degeneracy of vacua. And so I think if you're going to look for some effect, it's probably going to be in the degeneracy, the large degeneracy of those vacua.
But what goes wrong with the Feynman diagrams doesn't just randomly go wrong. Feynman diagrams tell you that you have got to look at multiple emissions, there's logs, there's things that go wrong. None of that is happening in this calculation. We just have you have massive particles, we do some graviton exchange, everything is totally perturbative, totally fine. There are no logs, there's no big effect. So I don't see the analogy. mean, if you just do the calculation, right, you just have, you have your interferometer arms, you have graviton exchange between them. There's no room for a large log in the vacuum. Where the large logs come from is, constant acceleration, you have like, none of that is going on here. You just have something going on.
Plus there's a factor of the entropy.
Sorry?
Plus there's a factor of the entropy that's relevant.
So that might be a physical fact about the correct theory. I'm just saying it's not like the analogy I think you're.
Yeah, no, I think if it were trivial, yeah, if it were trivial, then absolutely. It's all of this always happens because you have this factor of the entropy that's entering.
But it really is saying that the effective field theory is wrong, not that
Yeah.
So it's a radical statement. I don't think it's like it's not like.
I cringe a little bit whenever you say the effective field theory is wrong, because the words effective field theory, do I think that there may be a soft effective action that I can write down and I can compute some process?
I mean, naive effective field theory.
Yes, I agree with that, yeah.
And
Naive effective field theory would just give you the wrong
I
answer.
think I would agree with what Juan was saying at the beginning, that it would be the first example we've ever seen where the naive effective field theory is wrong. Or I don't think we've seen one example where the naive effective field theory for this kind of.
Well, how would you describe smoke spreading?
Sorry?
How would you describe smoke spreading with naive effective field theory?
I mean, just turbulent smoke.
Yeah. There's some things that are just not easy to describe with naive effective field theory, even though I would call it completely consistent with naive effective field theory.
Well, maybe this is related to a less technical way of saying the question, which I think.
That's what I'm saying, it's less technical. Smoke spreads, and there's interactions on very short.
Smoke spreads because there's a material there, and we've known since Einstein that there's no material in the vacuum. That's like that's another issue.
There are gravitational degrees of freedom here, right?
But this random walk intuition would tell you that, experiment by experiment, there's a jitter, right? There's some jitter. You go this way, you go the other way. That's not very Lorentzian. That's
Your detector picks out a frame.
No, but the thing is, all this
That's
jitter
right.
and stuff.
Your detector picks out a frame. That's absolutely right.
right, but it's
You can
not
look at the
translation
constant
invariant. You
development
do
of
the
a-
experiment at some different times, you do the experiment in different frames, you get a different answer. That's.
My experiment will tell you what the answer needs to be, because it will pick out a frame and it will tell me how to do the calculation.
No, but I'm saying something else. You repeat the same experiment today, tomorrow, next day, you're getting
I'll get it.
the jitter, you're gonna get a
Sample,
different answer.
yeah, I'll sample the distribution. It's stochastic.
But
and the
that's
reason for
somehow
that-
incompatible with the idea that the vacuum is translation invariant. Translation.
I don't think so.
That's the physical content of translation invariance. You get the same answer.
You're
When
saying
we do
that-
the same experiment at different times, you get the same answer.
Okay.
If you could measure all of the vacuum, that would certainly be true. And in fact, this effect goes away in the large L limit. Right? It's a mismeasurement effect. It's a vacuum mismeasurement effect. And so, yes, when I do the experiment different times, I get different answers because I'm not measuring the vacuum precisely. That's what's going on. So if I want to think about it from single graviton point of view, if I just measure this part of space-time, all the gravitons that are being emitted over that measurement period that have an energy less than 1 on L, I just don't measure. And the number of those gravitons that are emitted, which in this picture is set by the entropy, they give rise to a vacuum fluctuation, which is a mismeasurement effect.
But this seems like I like Juan's picture of the statement of like large logs. Like when we do effective field theory, like in the examples you gave, there's a signal that effective field theory breaks down from large logs. This is like, I think the example that I'm most familiar with is if I have a light field that's not derivatively coupled and consider. Like if I do naive effective field theory, it will be wrong because I have large logs and I need to resum the large logs. That gives me a coherent state, and then I do need to do perturbation theory around that coherent state. So maybe that's an example of where effective field theory fails, but this again, there's the statement of we have large logs tell us it should fail. Like you can do Polchinski analysis and just tell you that there's large log failure.
From the 1 on G Newton in here, which is to say from the large number. So if you take that seriously as saying it's counting the fluctuations in the gravitational degrees of freedom. In this case, that 1 on G Newton, which I don't know if you would call that a breakdown of EFT or not. I don't think I would, but it's not powers of G Newton. That's what's giving rise to this funny scaling, but there's a 1 on G Newton in here.
And so,
We discussed, I mean, I agree that that there will be fluctuations in the geometry of space-time and so on. But the way we compute this is through the Feynman diagrams, right? That's what this, that's the standard way of computing the effect.
Yeah, I know it's a standard, yeah, I know this is not the standard way of computing.
Well, but
In that case, you get, by the way, in that case, you get an infinite answer. So the quantity that starting with is actually divergent in field theory.
But we
It's
can-
the tr- it's what-
Not the quantity that tells you about the,
No, but the trace of the square of the expectation value of the modular Hamiltonian.
No, but
that's a different thing. That's
That
not
divergent.
computing, that's not computing the fluctuation.
So let me ask then a related question.
Yeah.
So you're writing down delta G is that square root. The actual equation is that the expectation value of delta G squared, which is the fluctuation, is L point over L. That's your equation, actually.
Well, this is what would come from this parametrics now. Like, I would say, you know, we can just calculate this now, even in flat space. You know, now, the question is whether it turns into the observable the way this back of the envelope would suggest. And so that comes down to whether, I mean, it comes down to several things. Whether this parametric estimate is just wrong in some way.
But the thing on the left, on the top left,
Yes.
question is, what do you really mean by the average, the double average that you're taking here? You're taking an average and you're taking an expectation value. Is this really the size of a quantum fluctuation?
Yes.
It's maybe less clear.
So the way that it has to be the case that this x plus x minus is actually a composite state. And so what I'm doing is computing the variance in this composite operator, and that composite operator, one way of representing it is the modular Hamiltonian.
So personally, I don't see too immediate objection to the top line. It would, I'm not sure if we computed it, but I wouldn't necessarily immediately claim that because I can imagine that there's an infrared, or at least that there are all these more subtle effects. The implication.
Yeah, I think
There's a jump between your first line and your second.
Yeah, so this second line, that's right, it's not the gauge invariant observable. What I'm explaining is why it is that these calculations parametrically give the scaling that they do. It's that you have the 4-point function of these shifts that go like G Newton. Okay. And you do not get that from a Feynman diagram. Definitely not a Feynman diagram just involving gravitons or even multiple soft graviton emission. It would have to come from a collective mode. And so if you're saying that there's no collective mode that would be representing this physics, I think we haven't proven, so the thing that we haven't proven yet is to just take this UV complete calculation and use the technology that one uses in gravitational wave experiments, which requires, and this is the rubbing point, it requires a global description of the metric. I have to be able to compute it along time-like trajectories and along null trajectories in order to compute the gauge invariant observable. Okay.
To me, it's a well-defined question, what the quantum effects are on the LIGO experiment. And we have a formalism that's supposed to answer this, which is vector field theory, Feynman diagrams, and so on, which we think would give a finite answer with no ambiguities. And just
yeah, and I think if you do the calculation, the single gravitons, and you do some Feynman diagram expansion, yes, that will not give this answer.
Right, so it will give a different answer, but that answer, I think, seems to be finite. And we could compute higher order corrections, which
will also be suppressed by powers of G Newton.
Right. So
this has to be.
So here you're doing some manipulations with a quantity that is not quite well defined. So, so that,
in what sense, not quite well defined?
Well, I mean, you had infinities. Not clear how you're defining K.
I think it's in what sense, like K has it's.
Well, the quantity modular Hamiltonian normally is defined, so you have some region on the boundary, right, where the metric doesn't fluctuate. And it's defined relative to this region. I don't, maybe it can be, I'm not saying it cannot be, there is fine, at least.
So the definition. That definition on top, you're saying is not well defined.
Okay, so normally when we say K, we modular Hamiltonian.
So in other
So that
words,
has a specific definition.
well, this
You could
is,
define it as the right-hand side of that formula. And
yeah,
okay,
and
that might be well defined. I haven't completely doesn't exactly
Yeah, I
define,
mean,
but perhaps it's well defined.
we'll be able, so that criticism I don't agree with. Because we're also going to be able to show that this quantity now is just the soft effective action. So we'll be able to write it down in terms of these Goldstone modes and the soft modes, and I think it will be a very well-defined thing. It is, and I still think even at this level, it's very well-defined.
Okay, maybe there is something well defined about K. So there is the definition of K. Maybe there's a way of defining it. But then the jump from K to the interferometer is
So I think that is the part that we have not nailed all the way through, which is to take these light ray operators, which are shifts. They are related to the metric. Okay, but even if you have but it's the metric on the light sheet. The metric on the light sheet. And incidentally, this is computed in a single causal diamond. That is not enough to compute the proper gauge invariant observable, because I also need to be able to compute what the metric is doing on the mirrors. Those are time-like trajectories. Okay, so if you want to make a criticism, that's the criticism to make. Okay, everything else up to that point I think is perfectly well defined. But if you want to make a criticism, which I will completely agree with, that is the criticism. So I completely agree. Like, this doesn't come from, calculating Feynman diagrams. And so it comes down to whether you really think the divergence that appears in these modular fluctuations, whether that can give rise to physical effects or not. Because it is that divergence, which corresponds to a large number of degrees of freedom, that then effectively amplify the effect. All right, so I'm going to skip through the rest of what I was going to say about this. You can make these statements, actually, you can look at fluid gravity. So one other thing I do want to say quickly is that it's well known that if you look at the near horizon limit, even in flat empty space, it has a fluid description. And that goes back to, there's a fluid gravity literature. You take the Einstein equation, you go to the near horizon limit, you get a fluid equation. And so this is a fluid equation now where there is a noise term. There's a quantum jitter. Now, with that quantum jitter being just fixed by the tough commutation relations. Okay. So if you just think about there being the Einstein equation, I just want to say that one other thing is that this works from a technical point of view in the sense that I can write down the vacuum Einstein equation, set it equal to 0, and then say, okay, I'm going to put in a noise term, which is just if I'm working in 4 dimensions, it's just a 4-dimensional delta function. And then, well, what do I do at a light sheet horizon? Well, what you can do is to say that light sheet horizon has some quantum width. Yes, that picks out a preferred frame, but it's a preferred frame that's determined by your experiment. Experiment has a preferred frame. And you replace now one of those delta functions with the width of that stretched horizon now. Okay, I'll stop. And that will give the same result. So that's another way of thinking about it. All right, so I'll stop. My computer is hung. But while I wait for the computer to is I think these two statements are independent of the observability. So the fact that these tough commutation relations are just equivalent to the soft ones, that was not known before, and we've just shown it now. And so then if you identify the boundary action with the modular Hamiltonian, you get an area law if you put in those soft commutation relations or the tough commutation relations. So I think these 2 points actually should not be controversial. I think this is the one, okay? And I will not claim that I have fully like hammered through to the observable, because that is a hard thing to do. You need the global metric to be able to do that properly. I have a model that reproduces those results, but I will say it's a model. So if we take these 2 points seriously and apply a memory effect that allows them to accumulate, then in that case, you would get potentially observable fluctuations. And it's not a Feynman diagram calculation. It's more like a fluid calculation. But I will say again, these gauge invariant signatures need to be studied in more detail and fully derived from first principles. Then I'll be fully confident that you understand everything about this setup and whether one would actually expect to see it. So thank you.